Today we'll be simplifying radical expressions. A radical expression uses a radical symbol to indicate that you want to find the root of the expression. In the setup, this is one of the most common symbols you'll see in movies and everything, showing off fancy math, is the root, the radical symbol. Now when there's not a number there, the index is understood to be 2, and the number on the inside of the root function, or the radical symbol, is called a radicand. Like I stated, the index tells us which root we are looking for. We understand if there's no number there, it's 2, but we can place any number in here to find that root. To find the indicated root of a number, we break the radicand down into its prime factors. To find the indicated root of a variable expression, we use the rational exponent rules. First, just to clarify what prime factors are. Prime numbers are values that are only divisible, or they only have 2 factors that can multiply to equal. The factors being 1 and itself. Some of the first examples of this are 2, 3, 5, 11, 13, 17, and 9. Each of these numbers, the only factors in what we're about to show you, a factor tree, are 1 and the number that they are. Now the way we will use this, all of our examples right now are just going to be the square root. So in this case, we are looking to see any matching pair of numbers and combining them in the end. What I mean by this is 36 is our starting point. If I break this down into its factors, I'm saying what 2 numbers multiply to equal it. I can make this a little bit more straight. Most of the time in these situations, you want to see if it's an even number. In that case, you know you can always multiply a number by 2 to find it out. So this would be 2 and 18. Now 2 is one of our prime numbers, so we are done with this one. We can go to 18 and break it down some more. Yet again, it's even, so I know that I can multiply a factor by 2 to get 18, which in this case would be 9. And we can break 9 down into 2 factors, being 3 and 3. Now, the bottom level of each one of these trees multiply to equal 36. We already know 3 times 3 is 9, which can multiply by 2 to get 18, which can multiply by 2 to get 36. Our goal here, since we are looking for the square root, is to find every matching pair of numbers. We have a matching pair of 2 and a matching pair of 3. With these matching pair, I am only going to write the number down 1 time for each pair that I have. In this case, it would be the 2 and the 3. Now, this prime factorization tree, this prime factor tree, is all about multiplying. So the pairs that we pull out are going to be multiplied to each other. Now, if I look at this, I have 2 times 3, which ends up being 6, which is the square root of 36. You can always check this in the calculator. All of your roots are available to be done in a calculator, but if you need to do it by hand, this is one of the simplest ways to confirm your answer. We can do the same thing for 441. What I like to do is start from the smallest prime numbers and move upwards. This is not an even number, so then I cannot divide by 2. I check to see if I can divide by 3, which I can, which would give me 3 and 147. 3 is a prime number, so then I would move over to 147. Yet again, it's an odd number. I can't divide by 2, but I can divide by 3, as all the numbers add up to equal a number divisible by 3. This gives me 3, yet again, and 49. Now I can go through the list to see what this is divisible by. It's not odds, or it is odd, so it's not divisible by 2. This one does not add up to equal a number divisible by 3. It does not end in 5 or 0, so it's not divisible by 5. The next prime number is 7. In this case, 49 is 7 times 7. These are all our prime numbers. So yet again, I want to circle any matching pairs. Write the number down one time for each matching pair. And multiply them together. 3 times 7 gives me 21. So the square root of 441 is 21. Now, for the most part, you can memorize your first couple of numbers in order. You can go from 1 to, most of the time, teachers will show up to 15 memorized. And then you can move a little bit further for your first couple of numbers. But there will be times where you run into numbers that do not come out perfect. They are not perfect squares. 20 is a prime example. No pun intended. So if we start with 20, it's an even number, so I know that I can divide it by 2, or 2 is a factor. In this case, 2 times 10 would give me 20. I can break down the 10. Yet again, it's even, so it would be 2 times 5. 5 is also a prime number, so I'm done. I have no more prime numbers no more numbers that I can break down. So yet again, I find any matching pair that I have. In this example, I have a number that is left over. Any values that are left over will stay in our radical symbol. So in this case, we had a matching pair of 2, so we wrote the 2 down one time. And our extra number that did not have a pair stays inside our root symbol, our radical. So in this case, my answer is a combination of the pair and the extra number. 2 times the square root of 5. To show a couple more examples, we can do it with 33. It's an even number, so I can break this down with 2 and 16. 16 is even, so I know it's multiple of 2. And this will be with 8. 8 is even, yet again. 2, 4. And last piece is 2 and 2. Now in this case, all the numbers are 2, but if we match them all up, we have 1 pair, 2 pair, and then we have an extra 2. So even though our 2's paired up, we still have that extra value. Our first pair for 2, our second pair, And then our final number that did not pair up. We look at this, that's 2 times 2. We can simplify that some more, which gives us the 4 square root of 2. Our last example, the square root of 35. In this case, it's not an even number, so we can't divide, or we do not have a factor of 2. Our digits do not add up to be divisible by 3, so it's not divisible by 3. It does end in a 5, so I know that I can divide it, or I have a factor of 5. Now this would be 5 times 7. Both of these numbers are prime factors. These are prime numbers. I cannot divide 7 anymore. I cannot divide 5 anymore. I do not have a pair of numbers. So in this case, the square root of 35 is in the simplest form. I cannot break it down any more than what it already is. Now at the bottom of my video, there is a calculator video for my class. This will show you how you can plug in the radical into your calculator to help you solve these problems outside of using the prime factor trees that we shown above.